Welcome to this explainer. Today, we're doing something really cool. We are decoding the actual mathematical models hidden behind everyday human decision-making. Think about it. We make countless choices every single day, constantly trading one thing for another. But how do we actually map out the logic behind those choices? Well, today we are going to break down exactly how economists visualize our satisfaction using geometry, focusing specifically on the properties of what we call an indifference curve.
I want you to pose this core problem to yourself for a moment. How do we map human satisfaction? It's a completely psychological concept, right? It's totally subjective. And yet, to really understand consumer choice, we need a reliable framework. We need a concrete way to visualize the trade-offs we make when we want more of one thing but have limited resources. Economists solve this brilliantly by using geometry. They map human trade-offs using an indifference curve.
Here is our quick agenda for today. First, mapping satisfaction. Then we'll hit the 4 specific geometric properties: the downward slope, the convex bow, climbing to satisfaction, and finally, why curves never cross. All right, section 1, mapping satisfaction. Let's lay down our baseline foundation. So here is the exact textbook definition we need to anchor our understanding. An indifference curve, which by the way is also known as an iso-utility curve, shows the various combinations of two commodities which give equal satisfaction to the consumer. The absolute crucial word here is equal. Imagine you're walking along this curve. Every single point you step on gives you the exact same amount of total happiness or utility, even though the actual mix of items in your basket is constantly changing.
Let's look at some raw data to see how this works in practice. Imagine a trade-off schedule between food and clothing. Look at combination A. You have 1 unit of food and 10 units of clothing. Now check out combination B. You have 2 units of food but only 7 units of clothing. You basically gave up 3 units of clothing just to get 1 more unit of food. Combinations C and D continue this exact trend. But remember our core definition. Whether you hold basket A, B, C, or D, your overall satisfaction remains absolutely equal. You're completely indifferent to which of these baskets you hold.
Moving on to section 2. Law 1, the downward slope. This brings us to our very first property. When we plot that data from our schedule, it reveals a curve that slopes downward from left to right. It has a negative slope. Now this isn't just some random drawing. It's a direct geometric reflection of human behavior when our resources are limited. The logic behind this downward negative slope is actually quite simple, but it's an absolute rule. To gain more of commodity X, which in our case is food, a consumer must accept less of commodity Y, clothing, in order to keep their satisfaction equal. Think about it. If you increased both food and clothing at the exact same time, your total satisfaction would obviously go up, right? If that happened, those new points just wouldn't share the same curve anymore. To stay on that same curve of equal satisfaction, one thing has to go up while the other goes down. Hence, the downward slope. Next up, section 3, law 2, the convex bow. Economic theory states this super clearly. An IC is convex to the origin. It bows inward to the origin due to the diminishing marginal rate of substitution. So this tells us that the curve doesn't just slope downward in a straight line. It bows cleanly inward towards 0. But why? The secret literally lies in that phrase at the end, the diminishing marginal rate of substitution. Let's actually break down that diminishing rate step by step using our earlier data. Moving from combination A to B, to get just 1 more unit of food, you were willing to give up 3 whole units of clothing. That is a substitution rate of 1 to 3. But to get the next unit of food, moving from B to C, you were only willing to give up 2 units of clothing. And for the next unit, only 1. As you acquire more and more food, your desire for even more food drops, and you become highly protective of your rapidly shrinking wardrobe. Because your willingness to trade is changing, the slope of the curve decreases from left to right, and that's exactly what creates that distinct convex bow. All right, section 4, law 3, climbing to satisfaction. Our third property states quite plainly, higher indifference curves yield higher satisfaction. An individual curve represents one specific, locked-in level of happiness. But if we were to draw a whole map of them, shifting the curve outward and to the right naturally brings more overall utility. Let's visualize what this climb actually looks like. Imagine combination A sitting on a lower curve. Let's call it IC1. Now imagine a second curve plotted above and to the right of it called IC2. If we pick a combination B on this higher IC2 curve, it represents a distinct increase in utility,
Why? Because basic geometry dictates that any point on that higher curve contains more of both goods. Combination B would specifically include one more food, and one more clothing. So the absolute crucial takeaway here is that moving to a higher curve means you are gaining more of both commodities. It represents a wealthier, decidedly more satisfied position.
Finally, Section 5. Law 4. Curves never cross. This is the final property that mathematically holds the entire model together.
Now ask yourself this. What would actually happen if two indifference curves intersected? We just established that different curves represent entirely different levels of satisfaction. What if you drew them on a map and they accidentally crossed over each other like a giant X?
Well, the answer is a total economic absurdity. As the theory states, a combination corresponding to the point of intersection would give two different levels of satisfaction, which is meaningless and irrational.
Let's summarize the foolproof logic of this non-intersection proof. We know each curve is a completely distinct level of satisfaction. If they crossed, that single point of intersection would be a shared coordinate. That means that shared coordinate would technically belong to a high satisfaction curve and a low satisfaction curve at the exact same time. It would mean equal satisfaction across entirely unequal curves. This literally breaks the fundamental logic of rational choice. You simply cannot look at a single basket of goods and say, you know what, this gives me exactly 10 units of happiness, but also exactly 50 units of happiness. It makes no sense. Therefore, by the laws of geometry and economics, these curves can never ever cross.
As we wrap up this explainer, I want to leave you with a thought. These properties, the downward slope, the convex bow, the higher curves, and the fact they never intersect, these aren't just abstract lines on a graph. They're the geometric representations of human desire and limitation. Every single time you budget your paycheck, balance your free time, or even just decide what's for dinner, you are operating on a hidden indifference curve. You are subconsciously measuring diminishing returns and mapping out your own satisfaction. So I have to ask, where do your indifference curves lie for your next major trade-off? Thank you for joining me, and keep questioning the mechanics of the world around you.